Hello friends, let's learn how attention mechanism works in large language model. Let's start. First thing first, where it all started. It all started with this particular research paper which came in 2017. I'm sure you must have seen this research paper before. But what exactly it proposed? It proposed a brand new architecture called transformer architecture. Now this particular figure on the screen may look intimidating, but we'll try to intuitively understand each of these boxes and to make the complete sense out of this transformer architecture. But our key focus in this particular video is to pay attention to how multi-headed attention or mask multi-headed attention works. So friends, we are trying to understand multi-headed attention, which is represented here, or mask multi-headed attention mechanism. But to understand that, we need to understand the transformer architecture itself at a very high level, right? So let's unpack each of these boxes and what they mean. First thing first, on the left hand side what you see is an encoder network. On the right hand side what you see is a decoder network. Our GPT based large language models are all decoder based networks. Okay. Now, what is the input over here? Input is nothing but a series of words or tokens. I'll be using the terms words and tokens interchangeably, but we'll pay more attention what token or word is little later. So input is that, and what large language model or transformer will do, it will predict the next token or next word, and then it will put the predicted word and token again into the input sequence and predict for the next token. This is how the cycle will continue. Okay, what is the input embedding? Input embedding is nothing but representation of a particular word or a token in a multi-dimensional space, vector space, right? Now, if that doesn't make any sense, don't worry. We are just going to unpack in the next slide also. After that, we come to multi-headed attention. Okay, and over here on the right side on the decoder network is also the same multi-headed attention which is present over here, and this is masked multi-headed attention. We'll see that. After that, what you are doing? We are doing addition and normalization. Normalization is again how the normalization typically works, like shrinking all the values between 0 and 1. After that, there are other layers of multi-headed attention, again addition and normalization. After that, there is a feed forward your deep neural network which is kept, again add a normalization. After that, a linear layer is there, and then softmax. Why softmax? Because we want to predict the probability, right, of what is the next token we should come, or we should come as the output, right? So okay, one thing which we missed was the positional encoding. What is this positional encoding? Now friends, since large language models or the transformer architecture in itself typically does all the tokens or words, takes all the tokens and words in parallel and processes it simultaneously. So if it does all things in parallel, then the sequential nature, what comes one after the other, which word came first, which one came after, that information is lost. To recover that information back, we do something which is called positional encoding, which retains the relative positional information of words or tokens into my input. Okay, hope all these blocks make sense at a very high level. But our key area of interest today is mask multi-headed attention, which will unravel. Okay, to understand this multi-headed attention or mask multi-headed attention, it's very important to recap a few things which we did in the last slide. Let's say with an example, the input text is the cat sat on the mat, and our transformer has to predict the next word or token in the sequence, right? This is the exercise. Now over here, for simplicity's sake, what I have done, I have taken this input which is a 6 word long, and then I have tokenized. By tokenization, I mean that I am breaking down this sentence or the input sequence of words into each word, right? So the D is one token, cat is another, sat is another, and go forth, and hence on henceforth. But the tokenization can be more complex than that also. Okay, so typically in a large language model setting, we use something which is called byte pair encoding. Now that is not what we are going to discuss today, But just for the time being, understand that tokenization can be done at a character level, at a word level, at a subword level, at a multi-word level. Like there are various options which are available for tokenization, but ultimate aim will be that our input sequence will be broken down into individual entities. Okay, so after that, now the our transformer will not understand this human text, right? It will understand only numbers. So we have to convert these tokens into a token ID. So this is like a representation of the in my vocabulary is at 1026 position. So I am giving it a number assigned to it, 1026. Cat is assigned a token ID 9004. Sat assigned a token ID as 54 and hence forth. Okay. Now comes the next step, which is embedding vectors. Now this is the part which you must have seen over here, the input embedding. So input embedding is a part of the transformer itself. And what it does is this 1026 9004, these token ID, they get represented into a multi-dimensional vector space, right? What is the importance of that? Why it is helpful? We'll probably park it for now. But you can go ahead and read why embedding helps in representational learning, right? But long story short, what it is doing is that it is representing these numerical token IDs into a string of floating point numbers, right? So 1026 or D is represented as 0.2, 0.6, 0.7. So this is a three-dimensional space. In three-dimensional space, in three-dimensional vector space, D is represented by these three numbers. So you can imagine in a coordinate geometry space, right? There is a particular point in that space which is locked for D, okay, and which represents D. Similarly, cat, sat, on the mat, everything gets represented. And these embeddings are being learned as part of the training itself in large language model or GPT type models, okay? Okay. Now, if you understood this, let's move forward. Okay, so I was talking about the tokenizations, right? So just I have put a quick slide over here that what are the different types of tokenization involved, right? Or which is available. So it can be various, right? Like from character to words to sentence level encoding, right? Sentence level tokenization, everything is possible. But what we typically use in a modern GPT type large language model, which is something called BPE, byte pair encoding over here, which you see, right? The byte pair encoding, okay? And I do not want to go into the detail, but you can read about it, or you can comment below that I should make another video, separate video for that, okay? Now, let's come to the stage one of this to understand the attention mechanism, okay? Now, to understand this, what we have done, we have created an embedding vector for each of our words. We have tokenized based on words for simplicity's sake. It can be subword also. And we have taken each of these tokens and created an embedding vector for that, right? A representation for that, okay? In a three-dimensional vector space. 3 is just a number. It could be multi-dimensional, right? Typically, it is more than 1,000 dimensions, okay? After that, what we are doing is that we are selecting or initializing rather 3 weight matrices. We call it WQ, WK, and WV. These are n cross m multi-dimensional matrices, right? They are initialized and their parameters of these matrices are learnable parameters which are learned by the model during the training, right? So when we are training our transformer models, these particular weight matrices are also learned, okay? Now, if these matrices n cross m dimensional matrices are available, in this particular case, to make the math simple, we'll keep the weight matrices as a 3 cross 3 dimensional matrices, okay? So that the math works out. And now, what is the embedding vector dimension? It is a row vector, 1 cross 3, 1 row and 3. So if you see, this is 1 cross 3 dimensional vector, right? And our WQ, WK, WV, which are learned during the training, is a 3 cross 3 dimensional matrices, okay? Now these Q, K, and V have a special names. Q stands for query, K represents key, and V represents value. We'll see that why these names are given to it, okay? But the first thing what we are doing is using these WQ, WK and WV matrices, we are creating our query, key and value triplet for each of our tokens, okay? So the was represented as 0.2, 0.6 and 0.7, right? Now we multiplied this 0.2, 0.6, 0.7 with a WQ matrix. Okay, so it's a vector and a matrix getting multiplied. And when a 1 cross 3 vector gets multiplied with 3 cross 3, the resultant, by our linear algebra, we understand that it will be a 1 cross 3 vector. So when we multiplied it by these weight matrices, we got a triplet of query, key and value row vector again, which is of a dimension 1 cross 3. And friends, remember, these 1 cross 3 and 3 cross 3 are very, very simpler examples, right? In the real world, it's much, much bigger than that, okay? Now, we similarly will get the query, key and value triplet for all the tokens, right? I have just represented it for 3, but we'll get it for all the tokens, okay? Now, the one which we got after multiplying our embedding vector with WQ is the query. Similarly, we'll get key and we'll get value. Okay. Till that, I hope it is fine, right? Now let's move on to next stage. We have got our query, key, value vectors for each of the tokens. In the next, what we are going to do, we are going to find the attention score. Attention score is nothing but a way to measure how much attention one token should pay onto the other. Okay, by that I mean, let's say SAT. How much attention SAT should pay on cat or SAT should pay to thee is represented by attention score. And this is the crux of the base idea about the self-attention mechanism. Okay. Now, how do we arrive at that? What we do is that for each of these tokens, we have triplet vectors, right? Query, key and value. So suppose we have to get the attention which SAT should pay to thee. SAT should pay to thee. What we'll do is we'll take the query vector. Okay. We'll take the query vector of SAT and we'll do a dot matrix multiplication or a dot product of SAT query vector with the key vector of thee. Okay. One more time. What we'll do is that we'll do a dot multiplication of SAT query vector with the key vector of thee to get how much attention SAT should pay to thee. Okay. And similarly, we'll do it for each other, right? So for one example, minus 3.1, 1.9, 2.3 into dot product of 2.1, 1.9 and 3.7. Dot product we know is that element-wise multiplication and then addition. So we did the element-wise multiplication over here and then we did the addition and we came 5.61. Okay, all well and good. So similarly, we'll create this for each. For SAT, there will be, for SAT, we'll have 6 such numbers, right? 5.61 with D. Then again, another number will come for cat, another number will SAT with SAT, another number will cat with SAT with on, and hence and henceforth. And so we can see that there will be 6 your attention score for SAT vector itself. Okay. Now this is the step 2 to get the attention scores. This is called the attention score. Now we'll get the attention score, as I was saying, that we'll get for SAT, we'll get 6 such attention scores, right? And similarly, you can understand that if we start getting it for each of the token, immediately we'll land up with 6 cross 6 matrix, right? So for SAT, we have got these attention scores. Similarly, for D, with respect to the other tokens, we have got these attention scores and hence so and henceforth, right? So we understood that how this 6 cross 6 matrix of attention score is built, right? We understand that. Now let's move on to step 3. Step 3 is to get from the attention scores to attention weights. Attention weight is nothing but a normalized score across the row. So we normalize our values which were there. These were unnormalized value, and we normalize. By normalization, what do we mean? By normalization, we mean that we shrink these values in a proportionate way to be between 0 and 1. And the way to do that is that this is the natural Euler number, E. It's the softmax normalization. If you know softmax, that's fine. Otherwise, what is there? This is the Euler number, E. E raised to the power this number divided by e raised to the power this number plus e raised to the power this number plus e raised to the power this number plus e raised to the power. So the denominator will e summation of e raised to the power individual numbers, and the numerator will be your e raised to the power individual. So you can see that we are getting it normalized in a softmax fashion. Okay. So what we'll do, it will shrink every value between 0 and 1, and the other thing will be that if you add all these values, they will be sum total to be 1. Okay. So now what we have done effectively is normalized, and these normalized attention scores are called attention weights. So we have got an attention weight 6x6 matrix. Okay. Hope till this point it is okay. Now let's move on. In step 4, what we'll do is we have gotten this matrix of attention scores. We'll do a causal masked attention. Now, what is this causal masked attention? We saw earlier in the diagram in the transformer architecture, there was a masked attention. What is this masked? Masked attention is nothing but a clever technique of that when I'm working with a particular token, I should hide what the future tokens look like, right? I should hide that particular information. And the way they are hiding is that they are above the principal diagonal, they are masking everything, or they are removing everything or setting everything to 0. Okay. By that, what they are doing, they are moving away, or they are hiding the future tokens from the present or the past tokens so that they do not see that. So the causal attention mechanism ensures that the model only factors in tokens that occur at or before the current token, right? Not after that, not the future tokens, right? So this is the step 4, which is called causal masked attention. Okay. There is dropout also, which happens at this stage, but I have kind of dropped that, right? But you can read about it. Okay. The last step, or the second last step, is to get the context vector out of it, right? Now we have a 6x6 attention weight matrix. We have hidden the top half of the diagonal, right, over there for the masked attention. Now we have to get the context vector. So what is the context vector? The context vector is nothing but the weighted mean, or the weighted way, or the weighted sum. Rather, it's the weighted sum of the value vector with respect to the other token. Now let's try to understand. Okay. So let's say we have to get the context vector for SAT. What we'll do, we have the attention weight of D with respect to SAT. We already have that. We'll multiply that value with the value vector of D. With the value vector of D, we'll multiply the attention weight of SAT with respect to D. Okay. Or the attention weight of D with respect to SAT. We'll multiply that. Okay. So what we are doing, we are taking the attention weight from the matrix, and we are seeing the value vector, okay, of a particular token, and we are multiplying them, and then we are summing each of them, right? So if we have to get the context vector for SAT, what we'll do is that with respect to SAT, what are the other attention weights, and then we keep multiplying with their values, the respective values, and then we are summing up. If we are multiplying it, so this particular attention weight is a scalar quantity. This is multiplied with a 1x3 vector. So all of these individual elements, 6 elements, will be 1x3 vectors, right? And when we sum them up, it will always be 1x3 vector. We result in a 1x3 context vectors. That's how the context vector is created. Once context vector is created, the last step is, which we are seeing, this is how one attention module is built, right? If we have to do a multi-headed attention, what we are doing is that we are stacking all these attentions in parallel, right? What we are gaining by that, we are gaining parallel processing, and we are, in a way, what we are gaining is that we are giving the chance to the model to learn various aspects of the language in a different attention modules, right? So let's say one attention module may be learning about the language dependency, one may be learning about the grammar, one may be learning about the like the subject and verb agreement, and there are various things. So in this particular picture, we have shown only two stacked attention mechanisms or two stacked attention modules, but it could be multiple. That's why they call multi-headed attention. So there are multiple attention modules stacked together in parallel and run through. Now, a couple of things to watch out for. One is that we know that these weight matrices are there, right? So for each of these attention heads, there will be separate weight matrices. So your WQ, WK and WB will be separate. The input will be the same. Okay, the input will be the same, but you can realize that my attention score and attention weight and my context vector all will change because my weight matrices are changing over here, right? And once all these are changed, for each of the attention module, I will get a context vector. What I'm going to do is over here it is represented only two context vectors, but in reality there will be multiple context, and all these are concatenated together. All these are put side by side together. So if there were two dimensional context vector for the first module, attention module, and again two dimensional for the second module, I'm concatenating it, putting it side by side. So I have a 1x4 dimension context vector, and this is how your context vector is generated, okay, for one particular token, and you generate for all the other tokens. And what you do after that, if you go back to your transformer, this is how your mask multi-headed attention context vector is done. And after that, you add and then feed it to normalize. You again normalize it, again pass it through multi-headed attention, add and normalize, and then you pass that whole context vector into the feed forward network. Okay, so that is beyond the scope of what we are discussing today, but I hope you understood what the mask multi-headed attention and how it works at a very, very high level, right? With a simple example, right? Okay, this is what it is. Okay, I hope you like this video. If you have any question, let me know in the comment. If you want me to make some more videos on these topics, let me know. I do teach data science and machine learning. So these are my coordinates. If you want to learn, feel free to ping me, WhatsApp me, DM me on LinkedIn, and I'll be happy to bring you into the next batch of my course. Okay, with that being said, thank you.